In this week's challenge, I'm going to recommend a couple of resources for additional learning. I haven't really covered much in theory as of yet. This may be best covered within some books, and I'll give you some recommendations for the books that I would suggest. But this particular assembly is from one of the books that I would suggest, and it is a representation of a Newton's cradle. The purpose of this isn't really to exactly duplicate the way a Newton's cradle would work. For one thing, these balls would not stay in a straight line on single strings. But the purpose of this lab is to demonstrate the various ways of putting in your constraints. For example, we have in the past turned off the automatic constraints, and then we manually put in our own constraints, so we can do manually or fully automatic. And I should use the term joints, not constraints. Or if I turn off the automatic conversion, I can either accept the joints that already existed or delete them. I'll go ahead and accept those or keep those joints. And then notice that there's also a convert constraint. So I can select two parts and use the constraints that are the assembly constraints that are between those two parts to generate the joints. And I can selectively convert those. And so all of this is covered in the book, which I'm going to recommend. And we can use what we learned to create some kind of mechanism. For example, on these, the balls are held back at an angle, and I'll go into dynamic simulation and we'll start playing this. And so this is a wave pendulum, and we'll see that the cycle period changes depending on the length of the connecting strings. And at some point it may look like it has become totally random, but if I go to the side view and look at this, and we'll continue to watch this, we'll see that it starts to develop additional patterns. I'll go back to looking at this from an isometric view. It doesn't look like it's achieved any pattern from that view, at least not at this time period. So the challenge then that I'm going to give to you is to come up with your own design for a Newton's cradle. So search the internet on images for Newton's cradle and pick one to reproduce, or you might make it a totally new design of your choosing. Here's an example. So this one a student did as a double Newton's cradle, and so we'll go ahead and play this. So I'll go to dynamic simulation and I'll put it into motion. Now, again, this was student work. It isn't quite valid. I'll let you try to experiment and find a valid solution. The mass on one side should be the same as the mass going to the other direction. So the references that I'm going to suggest are Up and Running with Autodesk Inventor Professional. This is part 2, Dynamic Simulation by Huei-Huang. Part 1 is on FEA, and then part 2 is on Dynamic Simulation. And so I'll go through here and look at the table of contents briefly. You can look at that, search for that on Amazon. I don't think we can read that too well on my screen. But anyway, so that's Autodesk Up and Running with Autodesk Inventor Professional Part 2, Dynamic Simulation. I'll put the link to these references in the description. For SolidWorks, this Engineering Dynamics Lab from SDC Publications, I don't know if this author has created a newer version, but the version of the book or the version of SolidWorks that was used doesn't really matter. And the problems, you could do them in any program. So even though this book is written for SolidWorks, you could reproduce the problems in Autodesk Inventor. This is my primary SolidWorks reference. I'm going to give you a secondary reference. My secondary reference is this book, Motion Simulation and Mechanism Design. And again, this is from SDC Publications. I prefer the primary reference that I gave you, but this is a good reference as well. And again, you can do the problems in Inventor or in SolidWorks.